Thanks everyone for coming, and thanks to the organizers for asking me to speak. I guess they wanted, to line up a few experimentalists after the theoretical talks this morning. I spent most of last week in a town called Kananaskis. Roger probably knows it, maybe. Anyway, it's in Alberta. These are all pictures taken over a few days there. You can see, this was actually taken by Louis Taillefer, some of you might know him. They were walking in the path of the mighty bear. This is aspen tree, which is, you can see that the bears were using it to teach their cubs how to climb. We didn't actually spot a bear, but we're pretty convinced by this evidence that bears exist. Okay. That's somewhat the idea of this talk. So I'll talk about some time permitting, if I can be fast enough. There's no way I can be anywhere near as fast as Shai was this morning. But I'll talk about a fairly advanced project begun with my student Zen Hao and a few others on the top row, and then if there's time, I'll talk a little bit about something that's very much in its infancy, which is a little more theoretical. I guess this is the first talk about quantum spin liquids. Probably to this audience, I don't have to say much about it, but just to say that these are an interesting class of non-magnetic quantum ground states of spin systems that we find interesting because they realize different forms of highly entangled matter that range from gap topological phases like the toric code to a more interesting, for me, I guess in this context of this program and this conference, various gapless states of a varying degree of mystery. We heard a lot about CFTs, so in this list, these Dirac spin liquids kind of fall into that category. Okay. So theoretically, we have a pretty large knowledge of these sorts of phases, what we would like to do is figure out how to actually find them. From my experience last week in Alberta, I was thinking about where one should be looking. I'm using a bear for the metaphor of the spin liquid. The first kind of question you might ask is, where is the right territory to look to find these spin liquids? Territories might be, for us theorists, might be models, or they might be physical systems. In the more experimental realm, I like to think of kind of three classes of different experimental systems where people have looked for spin liquids in varying degree of success. Relatively recently, we've seen amazing developments in these quantum simulator platforms like Rydberg atoms, superconducting qubit systems, etc. And these are great because you have an exquisite amount of control, and you can measure things that couldn't be measured anywhere else, but they're small. We're talking about typically at order 100 quantum bits. On the other end are real, let's say, experimental quantum materials, which you could actually hold in your hand and see, which are typically of the order of Avogadro's number of electrons. The problem is, a chemist makes it, and then you have what you have. If your chemist is very talented, they can exert a little bit of control on the system, but not so much. Somewhere in between, which is kind of a sweet spot in recent years, are these 2D materials, which have maybe 100,000, a million electrons in them. But you have quite a bit more control than solid-state materials. Kind of motivated by that, we were this intermediate category of systems. We started thinking a bit about recent developments in 2D systems called transition metal dichalcogenides. These are a bit like graphene. They're 2D two-dimensional kind of honeycomb structured molecules, but with two atoms instead of one. This leads to an asymmetry in the structure, and they have a very simple kind of electronic structure from the point of view of bands. They're really semiconductors, so they have some filled valence bands and empty conduction bands. And in particular, because usually they involve some relatively heavy elements, there's a large spin splitting among the valence band states here. So at a particular momentum, you have a unique state with energy closest to the band gap. In these systems, there's really kind of only one degeneracy of these valence band states. There's a valley degeneracy, which is locked to spin. So there's just kind of a twofold quantum degree of freedom associated with those electrons, which can play the role of spin. If you look at a bilayer of these TMDs, in particular, the simplest case is what's called a heterobilayer, so two different materials stacked on top of one another. Then in general, the bands in the two materials are not aligned. So the lowest energy states, that is the ones closest to the band gap, will predominantly reside in one material and not in the other. So in that case, we can kind of build a low energy model just out of these states, which are then perturbed by the proximity to the other material. So this is kind of the simplest case. Many authors, this is a kind of a smattering of papers from different theorists who did pioneering work in the theory of these 2D materials, have argued that you can describe these type of TMDs by an effective Hubbard model. So it's very simple. This is kind of the Hubbard model that we're used to, with the exception that these are really very strongly interacting systems on the scale of the Moiré pattern. And so in fact, it's important to consider longer range interactions, not just the on-site Hubbard, which is important in a lot of bulk condensed matter systems. So this is just motivation for us to actually look for spin liquids in Hubbard models. Okay. For the rest of this, I'm not going to say anything more about 2D materials. It's a theoretical problem. Okay. And I should say that there are a lot of also these 2D TMD bilayers which are not described by this, where there's some non-trivial topology in the bands near the Fermi energy. Particularly in homobilayers, you can't use this description often. Okay. But even though the Hubbard model is an old model, it's something like 60 years old now, it's a very hard model. And just to illustrate this, there'd be many, many ways to illustrate how poorly we understand the Hubbard model despite 60 years. I took this figure from a review article 2 years ago by Dan Arovis and company. Many, many extremely celebrated people are in this, authors of this article, and they've shown us phase diagrams of the Hubbard model. And despite 60 years, these are speculative ground state phase diagrams. Okay, 60 years of work on the Hubbard model, we still don't know what the phase diagram is. Okay, so that should give you an idea of just how hard Hubbard models are and why it's interesting to have a simulator for this platform. So there are already some amazing results in these TMD bilayers. This will motivate us looking at the theoretical model. Here are some experimental results on the left from Qinfei Mak and Ji Chen's group at Cornell. You don't need to understand really what's being measured here. It's a little complicated. Apart from to say that you can see what's being swept here is a gate, which is varying the charge density in this 2D system, and you can see an amazing structure of different responses occurring at different filling factors and different temperatures, different energy scales. And these are actually representative of a complex set of charge orderings that are happening. You think you have electrons in this sitting in some lattice, and as you're varying their density, they lock into different periodic patterns. And in fact, we know they can form kind of triangular or honeycomb superlattices or stripe patterns like this. They might even form some structure that looks like a Kagame lattice. If you look at the white sites here, you would see that this actually forms a Kagame lattice. You can think of this as kind of Wigner crystallization of these electrons in this 2D system. So these experiments pretty much only show you what the charges are doing, but electrons have spin. They're not showing us what the spins are doing. So as a theorist, we would like to understand that. Oh, I should say that by now there's also, I forgot I had another image here. There are actually some STM images that explicitly show you the periodic structure. So it's not just theoretical. So of course there's a lot of theory on this. I've learned to be afraid of 2D Moiré systems because people are working so fast and cranking out so many theoretical results. There's a huge amount of Hartree-Fock studies on these, espousing various different magnetically ordered phases. From the point of view of this conference, probably any magnetically ordered phase is boring. The good thing about these calculations is they're incapable of finding the spin liquids we're looking for. So they're sort of biased against them. So we'll come to it with the opposite bias and then try to find some middle ground. So what we did at first for this problem was to, as I said, take a theoretical approach which is actually biased against magnetically ordered phases and see if we can describe what's going on in this type of what you would call extended Hubbard model. So we take a very simple approach that dates back now, I guess, 20 years to some work by Serge Florenz and Antoine Georges. They propose a particularly simple parton construction where you write an electron operator in this Hubbard model as a product of a fermion, which carries spin, and a boson, which has no spin but carries charge. And this boson takes a particularly simple form of a quantum rotor. So it's just the exponential of a phase variable, which is conjugate to some number. To remove the redundancy of this description, you impose a constraint that the number of these fermionic spinons is equal to the number of electrons on the site. If you do this, then every time you have an electron density, you can actually just replace it by this number operator. And in doing so, you can basically write the Coulomb interaction, some interaction term, entirely in terms of the boson part of the theory. Then you need to somehow deal with the hopping term, which becomes complicated. And we do kind of a standard mean field procedure to split this hopping term into a fermion and a boson hopping. That imposes some mean field conditions, so we have to fix these effective hopping of the fermions and the bosons self-consistently. The physics of this, as I guess probably a lot of people in the audience know, everybody knows more or less, is that the phases of these hoppings become effective U1 gauge fields that kind of act to impose this constraint. As a practical matter, having done this, we still actually don't have an exactly solvable Hamiltonian. We have split the bosonic charges, and the fermionic spinons, but this boson Hamiltonian is actually equivalent to a quantum XY model with some long-range charging terms. So actually, to solve this practically, we do an additional mean field decoupling. So there's a lot of mean fields here. We'll see what comes out and then try to check it by some other means. So let me show you quickly a couple of mean field results. Here's a simple case where we take only nearest neighbor repulsion and no next nearest neighbor repulsions. And what you find, we're varying a chemical potential. So mu equals 0, the system is at half filling, and the strength of interactions. And you can see you get a bunch of different phases here. The ones that are marked with a specific value of n bar, these are all insulators where the charge density is fixed. It doesn't vary as you vary the chemical potential. Okay. But they're insulators, except for this one, they're insulators at some fractional filling that requires some enlargement of the unit cell. In between, there are some metallic regions where the charge density is not fixed. Okay. So this particular plot is made with a 3-site unit cell ansatz, which is kind of appropriate for that lack of further neighbor interaction. We can kind of decompose this diagram. Up here in the region where we have one electron per site, this is just a kind of simple mod insulator with 1 charge per unit cell per site. It's got too many clicks here. I stole this slide from Zen House, so I didn't realize how many clicks there are. Up here is is an insulator in which you can think there are singly occupied sites that form an effective honeycomb lattice. Here you have just a metallic state where the charges are uniform everywhere. This is another metallic state where the metallic regions form a honeycomb lattice. I'm not sure why this thing is circled. Okay. If we include longer range interactions, we get another more complicated phase diagram with some different regions. Now we get a region like this where the black sites, so this is a color code, by the way, for a bunch of slides. The black sites all have 1 electron per site on them, and the white sites, in this case, are empty. So you can see that the singly occupied sites form a Kagame lattice here. There's another region here where the singly occupied sites form stripes. Another region here, which is kind of a metallic Kagame lattice. A couple other metallic regions. Again, I don't know why the circles. Here I summarize all the phases that show up when we combine these things and try to find the lowest energy states. So there are a range of insulating states, ranging from one in which is just the usual mod insulator to a variety of what you might call commensurate Wigner crystal phases. This is a Kagame lattice structure. This is a honeycomb lattice structure. Here's some stripe. Here we have a kind of inverse honeycomb structure where you can see it kind of looks like the opposite of, I guess, this one, where the occupied sites just form a larger triangular lattice. And kind of in between these things, you get various metallic states. So these pictures only show you the charge. They don't show you what the spin is doing at all. Okay. But when you solve these mean field equations, you also get some understanding for what these spin-ons are doing. And that's actually more complicated. There are different choices that can correspond to the same charge mean field. Yeah.
So the mean field that you're doing, you get these. First, you solve the bosonic problem, the Bose-Hubbard model.
Well, you have to self-consistently solve. So you solve the Bose-Hubbard model for some set of hoppings, which are self-consistently determined from the some fermion band structure problem, and at the same time solve the fermion band structure problem for the using effective hoppings which come out of the boson problem.
KIJ is some fermion hopping.
Yeah, KIJ is related by a mean field condition to the fermion hopping. It's right, it's here. I just thought this was too detailed to...
You solve the fermion problem in that trial.
Yeah, so once we assume some unit cell, then we can just find a complete set of self-consistent equations and solve it. It's very much like a usual mean field. Okay, too many things. I don't want to go back again. We're not going back. Too much clicking. Okay, but basically, within a given charge order, we have a lot of solutions, actually. And this is something well known from old mean field theories of spin models, that at the pure mean field theory level, almost always the lowest energy states are dimerized states. So in these states, actually, the fermions don't hop in a connected pattern over the whole lattice. They have non-zero hoppings between some pairs of sites and zero otherwise. So they just form kind of localized resonances where they hop back and forth among pairs of sites. And we can get various different patterns that show up as ground states, at least stable mean field solutions in different doping regimes. Okay. However, there are competitive, energetically competitive solutions very nearby. So this is kind of well known for the triangular lattice Hubbard model. That a competitive solution is this kind of staggered pi flux state. If you look at the mean field energies of different states, you can see this blue one is this pi flux state that gives rise to Dirac points in the spectrum, and it's just slightly above the energy of dimer states. So this mean field solution, if you look at the fermions, it has a pair of Dirac cones within the Brillouin zone, these two yellow points here. So this gives rise to kind of two-dimensional Dirac cones. Each one has a spin degeneracy. In general, in total, there would be 4 flavors of these Dirac fermions in this state. And so we'll come back to this, hopefully if I'm not too slow. The last part of the talk, I'll talk about the effective field theory describing this, which is this QED3. I should speed up. The clicking is taking too much time. In the honeycomb lattice, we also find a Dirac fermion state is competitive and close to that of the VBS state. This one's believed to be unstable without fine-tuning. And in the Kagame, again, much as many variational studies found for Kagame-Heisenberg models, again, this is actually happening in the full Hubbard space, okay? We again find a competitive Dirac-like state. But, you know, I think everyone should be skeptical about these mean field calculations. They give you some idea of trends. And in addition, we've explicitly thrown out all the magnetically ordered states. Okay. So to try to do better, we could try to improve the mean field by, for example, projected wave function calculations. But instead, what we did is turn to my friend Hongchen Zhang at SLAC, who's an expert in DMRG, and just looked at some of these problems numerically. Okay. Clicking again. So what I'm going to do is summarize a lot of calculations by these kind of pictures. Okay. These are big calculations. It's only really been possible Hubbard models, which have this very large Hilbert space on relatively wide cylinders. These are all 6-leg cylinders, Hubbard models, done with both U1 and SU2 DMRG to check for consistency. The top panel are showing the charge density, and the bottom panel is showing the spin density. Again, the color code is black, means singly occupied site, or close to single occupancy. Okay. So here at 4/3 filling, we can see this is kind of relatively strong interaction. We always focus on this kind of limit. You can see actually a honeycomb pattern of charges. But compared to the spin liquid kind of ansatz that we made, actually, this system is magnetically ordered. Okay. You see a clear pattern of spin ordering, up spins and down spins, red's up and blue is down. They form this kind of what is usually called a zigzag order on the honeycomb lattice. I told you there was another state, this kind of inverse honeycomb, where you can think that there are singly occupied states that form this larger triangular lattice. Now, compared to the previous case, there's actually no magnetic order observed in the bulk here. There is some kind of boundary effect that turns on, but extensive search for any type of broken symmetry in the bulk doesn't show anything. So this one seems like a reasonable candidate for a spin liquid. 5/4 is kind of the most interesting case for us. It's the case that corresponds to the Kagame lattice in strong coupling. Here is a simulation with no second neighbor interaction. And this is a little bit intriguing. I wouldn't say we fully understand this result. But if you look carefully, you can see some charge modulation showing up here. But actually, and if you look at the scale, it's quite a small modulation. The charge density varies between 1.2 and 1.35. And the spin modulation is actually larger. It forms some kind of stripy spin pattern. Okay. The situation where you have a larger spin modulation and smaller charge modulation, that naturally corresponds to something more like a Fermi surface instability. I think we can understand the charge order as a kind of secondary order parameter that arises as a consequence of the spin order. Everything is consistent with that. This is some kind of collinear spin density wave phase. When we put in some further neighbor interaction, we get a real Kagame charge ordered state with a much larger charge modulation. And in this state, there's no spin order. In fact, all the correlations decay exponentially at a rate which is very similar to that in just the Heisenberg model on the Kagame lattice. So this looks very consistent with some kind of spin liquid state. We haven't put in the hard work to really determine what type. Oh, I should say also there's no dimer order. No, we couldn't find any order. Okay, how long do I have? About 5 minutes, okay. So that the second half hour of the talk, we'll change gears. And I want to talk about something quite a bit more speculative, but for me more interesting, which is, okay, suppose we actually figure out where in the terrain to look for our spin liquid, but we might not be so lucky as to actually spot it. Still, we could hope to find some indirect evidence of the spin liquid looking for its tracks. Perhaps we're just scared of the bears. Okay. So what we need to do is try to figure out how to identify the tracks. So I'm going to focus on the case of what seems to be the most prevalent quantum spin liquid in all these variational calculations, as well as many DMRG calculations, which is this Dirac spin liquid state. So this is really a condensed matter realization of three-dimensional quantum electrodynamics interacting with a set of Dirac fermions. There's a very nice review article from Shui Yang, one of the speakers later in the week. This model arose, I think, first among the study of spin liquids in the context of the Kagame lattice and some seminal work by Patrick Lee, Xiaogan Wen, Ying Ran, and others at MIT. There's some beautiful calculations from Yassir and Federico Becca that have really shown over and over again how strong a candidate this state is in quantum spin systems. There's some beautiful recent work on the triangular lattice by Alex Vitek and collaborators that really took this a step further and made a correspondence between many, many eigenstates of this lattice spin system and QED3. And this is a recent experimental report claiming to identify at least consistency with this Dirac spin liquid in this terbium compound. However, if you take a look at this plot, this is experiment and this is theory, it looks kind of okay, but these are very, very coarse things. It could hardly be called a smoking gun, and the theory calculation is not a calculation for QED3. It is a calculation within a lattice model. I think of this QED3 effective field theory for a Dirac spin liquid as some kind of framework that can describe many different physical systems. For example, we think it could describe a triangular lattice, a Kagame antiferromagnet. Maybe we can put the deconfined quantum critical point in this framework. Shui Yang will talk, I guess, later this week about her very recent work with Senthil as a description of some unnecessary quantum critical point. Each application uses a QED3 as an underlying theory, but it has its own microscopic set of symmetries. It has its own dictionary. Different operators in the field theory correspond to something different in the physical system. And each one has a different set of perturbations. Okay. But we can hope to try to find some signatures that are general. And as somebody who spent a lot of time in magnetism, I always turn to my friend in experiment, which is applying a magnetic field. It's a knob that's available in every spin system, and it's usually very informative. For example, you can trace out these kind of magnetization profiles as a function of field, and you see various characteristic features. For example, magnetization plateaus tell you something very interesting about the quantum spin system. This is a system with a spinglet ground state at zero field, and it actually has a zero field plateau. That's indicative of a spin gap. Usually these regions where the magnetization has a finite slope at intermediate values of field indicate some symmetry breaking, but not necessarily. So we can ask just for a proof of principle, what are we trying to look for here? This Dirac spin liquid is kind of an example of a gapless, non-trivial phase that doesn't have any symmetry breaking, doesn't really have any quasi-particles per se. And there are simpler examples of such conformal field theories. The simplest one is probably the 1+1 dimensional Ising conformal field theory. So this is realized, for example, in a Ising ferromagnetic spin chain in the application of a transverse magnetic field. It's a kind of course, grad course, maybe undergrad course, homework problem. We could do it in class to show that there's a phase transition at a particular value of the transverse field. So that's our kind of spin liquid or bear in this analogy. But actually, in experiment, it's not so easy to identify that directly. what was really done in probably the most beautiful experiment on this type of system is to identify the tracks of this CFT by applying a longitudinal field. The longitudinal field actually destroys the quantum critical point. It renders that CFT gapped, but it gaps it in an interesting way. So this was measured by Radu Koldea and collaborators now 14 years ago. What happens in that system is remarkable. The continuum splits up into a set of sharp resonances, which have this amazing property. They have this emergent E8 structure that the ratio of the energies of the two lowest bound states should equal the golden mean. And this actual ratio was measured, thank you, in this beautiful experiment by Koldea. So this is just a kind of proof of principle that you can uncover, something much more non-trivial than just some featureless continuum in this type of experiment. So what we'd like to do is try to seek similar things in QED3. The short answer is I don't know the answer. Okay, this is kind of a program that we're engaged in to understand this, but there's some beautiful physics which has already been predicted by some work already, how long ago this was? 2009, okay, so 15 years ago, by Yingran and company at MIT. So the physics you should think about is interesting. So QED3, as we heard this morning, it has two sets of symmetries we need to think about. One is, in this case, is some SUN symmetry, which is just rotations among these fermions. There's also a topological symmetry associated with conservation of flux in the theory. When we couple QED3 to a magnetic field, our magnetic system to an external field, we explicitly couple to one of these conserved charges of the internal SUN symmetry. And so we tune the value of this conserved charge by the field. However, the system itself chooses the value of this conserved flux. So in general, the energy of the system will be a function of these good quantum numbers, the SUN quantum number and the flux. And by tuning the field, we vary the preference for this magnetization. What Yingran and company showed was that actually it's energetically preferential, at least at mean field level, that in the presence of the non-zero magnetization, the system develops a non-zero flux. And this is actually a spontaneous symmetry breaking, because the flux could be either positive or negative. Okay, I should try to wrap up. They made some beautiful arguments about what this means. We believe it's actually resulting in a magnetically ordered state. That's a little bit boring, the sound of it, but it's in the same sense that the turning on a longitudinal field in the Ising model results in a fully gapped state. We're interested in structure within that fully gapped state. So the question we want to ask, and I don't have a good answer for you right now, is whether we can see signs of the QED3 structure within this induced ordered state. So I'll just kind of skip how we do this, other than to say that we have a kind of proof of principle in a one-dimensional analog where we really understand everything completely, that you can see such a structure. What might we be hoping to see? Well, this is very much a mean field plot, but what we might hope to see is something like this. This is kind of mean field calculation of the spin structure factor in the vicinity of k equals 0, and what we see is some kind of Landau level structure. That would be the kind of beautiful signature to look for in an experiment. So there are lots of open questions. I don't have time to talk about them. Maybe I should, I'd be happy to discuss with anyone. I'll just leave it here. Okay, thanks.
Are there any questions?
For this Landau level structure to emerge, do you couple to external field just Zeeman term, or you need something more?
Yeah, that's what's interesting about this. You only couple to a Zeeman term. So
no spin chirality, nothing like that.
No, there have been suggestions to couple in such a way to a magnetic field, but for real spin systems, this is not very reasonable. So the beautiful thing is that just coupling to in a Zeeman sense, only coupling to the SUN induces this flux. It's sufficient to do this. One of the nice things to mention about this problem is that actually there are, one can really study this at the level of the lattice gauge theory. There's a formulation of this which doesn't have a sign problem, even in the presence of the Zeeman field, which of course would not be the case with an orbital field.
Just following up on that, how does the cyclotron frequency relate to the Zeeman energy? Like, there's some proportionality constant there. What controls that?
Yeah, so if you optimize the energy, that's a universal ratio. It's kind of what you would expect because the CFT has no scale, and the only scale you introduce is introduced by the Zeeman field. So you find this plot, I made a plot somewhere, let's see, earlier. This is not a sketch. This is the actual, this is quantitatively what it should be. So this, yeah, so what I'm showing here are the up and down spin Landau levels. So the separation between those two zeroth Landau levels is the Zeeman splitting, and this is the cyclotron energy. Okay, so this is to scale. It makes a difference, right? It tells you whether the first Landau level of upspin is below or above the zeroth Landau level of downspin, for example. So this makes it definite. Yeah, there's a number. I don't remember the number, but.
And it's linear in H?
Yes, yes, yes.
Ben?
For the first part, excuse me, for the first part of your talk, you presented both mean field and DMRG results. I was wondering if you could comment on when those results are consistent with each other and if there's any sort of rule of thumb for when we can expect the mean field results to be reliable.
You know, we haven't done it's much easier to do the mean field calculation than the DMRG. So the DMRG, we're really picking a few points in the phase diagram. What I can say is that there's inconsistency for the less frustrated situation, okay? And we see also some other states at kind of intermediate coupling, like I showed you the spin density wave phase. This doesn't appear in the mean field theory. Seem to be, once you're kind of somewhat into the mod insulating phase, things look fairly consistent.
Yeah, for the last part, can you dope the system so that it have charge fluctuations? You know, your phase diagram, we have different rational filling, which is insulator.
Oh yeah, yeah.
Yeah,
oh,
then
yeah,
how
so
easy
that's not the last
to
part,
to dope it and to make a charge fluctuation. Then you may get a superconductor from this mechanism.
Yeah, you mean in DMRG, for example, or the?
No, in this mean field.
In the mean field. Yeah, the mean field is
similar.
I mean,
when you dope it, you have similar mechanism. You get a superconductor.
Yeah, I'm afraid I'm going to end up going through the click thing. I won't show you. But yeah, the mean field, we also have incommensurate densities. We have metallic phases in there. That mean field would not allow a superconductor. I think one would have to do fluctuations around the mean field to see that, but I think it's possible. Yeah.
I see.
Yeah, but we certainly have those doped phases. Yeah, yeah. Go back.
Do you expect signatures of this emergent Landau levels and things like just magnetization? Should there be like anomalous behavior of simple quantities like magnetization because of that stuff?
Yeah, you know, this is sort of the obvious thing to look for, but it doesn't happen at lowest order. So what happens is that the flux is actually changing with the magnetization in such a way that you maintain filling of a zeroth Landau level. So to get the kind of thing you might naturally want to look for are quantum oscillations. That requires a Fermi level to move through Landau levels, and that's not favored. Okay. So that's why we want to look at the structure of excitations. Although, you know, it's possible that if you leave a little bit the scaling regime, something like that might show up. So we're trying to look at these Monte Carlo simulations where we might see something like
Yeah, so I know you don't want to go back, but
I can do it on the keyboard.
you had a number of phases where the charge density wave and the, I don't know if you call it spin density wave or the spin order anyway, they didn't look commensurate at all.
They're
Maybe I
commensurate.
missed it.
They're commensurate, maybe hard to see. You're talking about in the DMRG?
Yeah, especially the first one, I think, the kind of more boring one, actually.
Let me go back here. This?
Yeah.
This is commensurate. This really, if you were to erase all the non-black sites, just you have a honeycomb lattice, and this is actually this kind of zigzag order, which actually the most commonly found on many honeycomb lattice materials. All these KITP materials tend to order like this. I think the least obvious one is probably this one.
Yes.
But this is also a commensurate spin density wave. Takes a long time staring at it to see it, but let's see. I think if you look at this line, you can see these are kind of Bragg planes. There's a question.
Actually, have you tried to put in, just to make some estimate of what will be the characteristic scale of the spin liquid behavior, given numbers for TMDs?
I want to say no. Okay, so it's an interesting question. In general, we can ask, it's associated with the scale of antiferromagnetic correlations. Okay, so you can ask, I think the simplest question you should ask is, can you see antiferromagnetic correlations in these Hubbard model simulators? And that's a relatively recent development, but indeed they can see that in at least the half-filled.
But is there a reason to expect there will be on this, like you will see some Curie-Weiss behavior and then the signatures of spin liquid-like behavior, would they come at the same scale or
Yeah, so
lower?
the point, there's a general trends we understand from these Hubbard-like systems that if you're close to the point of the metal insulator transition, these scales are comparable. As you go deeper into the mod insulator, you start suppressing these kind of spin liquid scales. So the sweet spot, that's one of the advantages of these systems. You can kind of tune them to be somewhat near that boundary, but yeah.
So of course, Hongchen has data on the Kagome spin half, just pure spin half, right? So how does it compare?
It's a very good question. I was scrambling to try to get that data to compare. I only can say at this point qualitatively looks similar, but I think we should be able to actually ask quantitatively. Yeah, so I failed to get it in time for the talk.
Okay.
Yeah, right. It's a good comparison. Yeah.
Any more questions? Well, it's time anyway, so let's thank Leon again.